There is a point in the universe where reality quietly refuses to answer. No matter how powerful our tools become, no matter how far curiosity pushes us, there exists a boundary beyond which nature simply stops revealing detail. Not because we lack technology, but because something deeper pushes back. This boundary has a name, the Planck length. It is so unimaginably small that even if you zoomed into a proton, then kept going smaller by a factor of 1 billion, and repeated that process again and again, you still wouldn't reach it. And yet, this tiny scale may define the ultimate limit of reality itself. But here is the unsettling part. The closer we try to look, the more the universe resists. In one of our previous Velaran journeys, we explored how black holes quietly erase information at their horizons. That same strange behavior, that same silence, appears again here, not in distant space, but in the smallest structure of existence. Because to see something smaller, you need higher energy. And when that energy becomes too concentrated, it does something unexpected. It bends space, then it traps light, and eventually, it hides everything you were trying to observe, as if reality itself closes its eyes. Tonight, we begin a slow descent into this mystery. Not rushing, not forcing answers, but gently unfolding the question that has followed physicists for generations. Is the Planck length truly the final wall of existence, or just the edge of something we are not yet able to understand? Before we drift deeper, take a quiet moment. If this calm corner of the universe brings you a sense of stillness, consider subscribing, leaving a soft like, and turning on the bell so you don't miss future journeys. You can also join as a member if you'd like to support these stories. And I always enjoy reading where you're listening from, whether it's late at night or somewhere between dreams. Now, let's continue. Because if the universe stops us from seeing deeper, we have to ask why. If you've ever looked at something through a camera and tried to zoom in too far, you may have noticed a strange effect. At first, the image becomes clearer, more detailed, and more revealing. But then, beyond a certain point, everything begins to blur. The sharp edges dissolve, the structure fades, and what once felt precise becomes uncertain. Now imagine that same idea, not in a camera, but woven into the fabric of reality itself. Because in the universe, clarity has a cost, and that cost is energy. To understand this, we begin with something gentle and familiar. Light. Every image you have ever seen, every color, every shape, has arrived through waves of light entering your eyes. But light is not just brightness. It has structure. It moves in waves, and each wave has a length, a distance between its peaks. This length quietly determines what light can and cannot reveal. Larger waves glide smoothly over small details, unable to resolve them. Smaller waves, with tighter spacing, can trace finer structures, revealing what was once hidden. This is why visible light, the kind your eyes detect, cannot show you atoms. Its waves are simply too large. They pass over atoms the way ocean swells pass over pebbles on the seafloor, never truly interacting with their fine details. So if we want to see something smaller, the solution seems simple. Use smaller waves, shorten the wavelength, increase the energy. And this is exactly what science has done. First with ultraviolet light, then X-rays, and eventually with something even more surprising. Not light at all, but matter itself. Because in the quiet logic of quantum physics, particles like electrons also behave as waves. And unlike light, their wavelengths can be adjusted with far less energy. By accelerating electrons, scientists can shrink their wavelength to match the scale of atoms, allowing them to reveal structures that light could never touch. This is how electron microscopes opened a new window into reality, showing us the arrangement of atoms, the patterns of crystals, the delicate architecture of molecules. But even in this success, the deeper rule remains unchanged. To see smaller, you must increase energy. It is a law that feels simple, almost innocent. Yet hidden inside it is a tension that grows with every step inward. Because every increase in energy does more than sharpen our view. It changes the system we are observing. At low energies, this effect is gentle, almost invisible. The act of observation barely disturbs the object. But as the energy rises, the disturbance becomes harder to ignore. Photons can knock electrons out of atoms. High-energy probes can break nuclei apart. The very act of looking begins to interfere with what is being seen. This is where the story begins to shift. Not dramatically, not all at once, but quietly. Because the deeper we look, the more we realize that observation is not passive. It is an interaction, a negotiation between the observer and the observed. And at small scales, that negotiation becomes delicate, almost fragile. If you push too hard, you don't just reveal structure, you destroy it. And yet we continue to push, because every time we have dared to increase the energy, the universe has rewarded us with deeper layers. Atoms gave way to nuclei. Nuclei gave way to protons and neutrons. And those, in turn, revealed quarks, smaller building blocks bound together by forces so strong they defy ordinary intuition. Each layer felt like a final answer, until it wasn't. Each discovery opened another question, another hidden depth waiting just beyond reach. But now, as we continue this quiet descent, something begins to feel different. The pattern that once promised endless discovery starts to show signs of strain. Because energy is no longer just a tool for seeing. It is becoming something else. Something heavier. Something that begins to affect not just particles, but the stage on which they exist. Space itself. And as we move forward, this gentle rule, that higher energy reveals smaller detail, will begin to twist into something unexpected. Something that does not simply limit our vision, but turns it against us. And so we continue, slowly, carefully, following the same rule that has guided science for centuries. But now with a growing awareness that this path does not stretch infinitely inward. Somewhere ahead, hidden in scales too small to imagine, the universe is waiting, not to reveal another layer, but to change the rules entirely. There is something almost hypnotic about the idea that reality can always be revealed, layer after layer, as long as we are willing to look closer. For a long time, this belief guided physics with quiet confidence. Each time we increased the energy of our instruments, the universe responded with structure. Hidden patterns emerged, deeper building blocks appeared, and what once seemed fundamental became just another stepping stone. It created a sense of momentum, as if there were no true end, only finer and finer detail waiting patiently beneath the surface. But as this journey continued, a subtle imbalance began to grow, not in the theories themselves, but in the cost required to sustain this deeper vision. At the scale of atoms, the balance still feels manageable. Electrons, moving with carefully tuned energies, can map out atomic structures without tearing them apart. The interaction is precise, controlled, almost respectful. But when we push further inward, toward the heart of the nucleus, that balance begins to shift. The energies required no longer feel gentle. They rise dramatically, not by small increments, but by vast leaps. To explore the interior of a nucleus, scientists must accelerate particles to energies millions of times greater than those used to study atoms. And when those particles collide, the interaction is no longer delicate. It becomes violent, energetic, transformative. Inside these collisions, something remarkable happens. The objects being observed do not remain intact. They fragment, scatter, and reveal their inner structure only through the traces they leave behind. This is how quarks were discovered, not by directly seeing them in a quiet image, but by analyzing the aftermath of extremely energetic impacts. It is a very different kind of vision, one that does not rely on gentle illumination, but on reconstruction. Like listening to echoes in the dark and inferring the shape of what made the sound, physicists learned to read the patterns of scattered particles to understand what lay inside. And this method works beautifully up to a point. The deeper we probe, the more the universe reveals, but always through increasingly indirect means. The clarity of an image is replaced by the interpretation of data. The certainty of seeing is replaced by the probability of what might be there. And still, the rule remains intact. Higher energy reveals smaller structure. It is a rule that has not failed us, but it has begun to demand more than we expected. Because every increase in energy brings with it a new kind of consequence. As energies climb higher, the distinction between observing and creating begins to blur. In low-energy systems, we observe what already exists. But in high-energy collisions, something else happens. New particles appear. Energy transforms into matter, briefly forming entities that did not exist before the collision. These particles flicker into existence and vanish almost instantly, leaving behind only traces in detectors. It is as if the act of looking has become so intense that it begins to generate reality, not just reveal it. This shift is subtle but profound. It means that at extreme scales, we are no longer simply uncovering the structure of the universe. We are participating in it. The line between measurement and creation dissolves. And with that dissolution comes a deeper question. If observing something requires enough energy to create new phenomena, how can we be sure we are seeing what was already there, rather than what we have just produced? This question does not yet stop us, but it introduces a quiet uncertainty into the process. A recognition that our tools are no longer neutral. They shape the very reality they are meant to explore. And as we continue to increase energy, this effect grows stronger. The collisions become more extreme, the outcomes more complex, and the interpretations more subtle. Yet through all of this, one idea continues to guide us forward. If there is a deeper layer, we will find it by pushing harder, by going further, by increasing the energy once again. But now, a new tension begins to emerge, not just in the systems we observe, but in space itself. Because energy is not just a tool for probing matter. It carries weight, it has presence. And according to the deeper laws of the universe, energy and mass are interchangeable, two expressions of the same underlying reality. This means that when we concentrate energy into a very small region, we are not simply sharpening our probe. We are increasing the gravitational influence of that region. At first, this effect is so small it can be ignored. Even in powerful particle accelerators, gravity remains negligible compared to other forces. But as we imagine pushing this process further and further, beyond anything we can currently build, a quiet realization begins to form. If energy continues to increase without limit, then its gravitational effect cannot remain small forever. At some point, the energy we use to observe will begin to curve the very space in which the observation takes place. And this is where the familiar rule begins to turn. The same energy that once revealed structure may eventually begin to hide it. Not by destroying it, not by overwhelming it, but by changing the geometry of space itself. The closer we try to look, the more we risk altering the stage on which reality unfolds. And somewhere ahead, though we have not reached it yet, lies a threshold where this effect is no longer subtle, where it no longer whispers in the background, but takes control of the entire process. For now, we stand just before that threshold, still guided by the belief that deeper understanding lies ahead. But the path is narrowing, the cost is rising, and the universe, once so willing to reveal its layers, is beginning to respond differently. Not with new detail, but with resistance. As we continue this slow descent into smaller and smaller scales, something begins to change in the tone of the journey. Earlier, each step inward felt like a quiet unveiling, a gentle peeling back of layers. But now, the deeper we imagine going, the more the process begins to feel strained, as if the universe is no longer simply revealing itself, but reacting to our attempts. The rule still holds, at least on the surface. Higher energy allows us to probe smaller distances. But beneath that rule, another one is beginning to rise, less obvious, yet far more powerful. To understand this shift, we need to revisit a simple but profound idea. Energy is not just a tool. It is not just something we use. It is something that exists, something that occupies space, something that influences the world around it. In the framework of modern physics, energy and mass are deeply connected. They are not separate things, but different expressions of the same underlying reality. This means that when we concentrate energy into a tiny region, we are not simply sharpening our probe. We are, in a very real sense, adding mass to that region. At everyday scales, this effect is so small that it disappears into the background. The energy in a beam of light or a stream of particles is far too weak to noticeably curve space. Gravity remains dominated by massive objects like planets and stars. But as we imagine pushing energy to extreme levels, something subtle begins to grow. The region we are probing is no longer just a passive stage. It begins to respond. Space itself starts to curve, ever so slightly at first, almost imperceptibly. This curvature is not a force in the traditional sense. It does not push or pull in the way we might expect. Instead, it reshapes the geometry of the space in which everything exists. Paths that were once straight begin to bend. Distances that once felt fixed begin to shift. And all of this happens quietly, without warning, as a natural consequence of concentrating energy. At first, this might not seem like a problem. After all, small distortions can be accounted for. Physics is built on the ability to correct for such effects. But the deeper we go, the more energy we require, and the more pronounced this curvature becomes. What was once negligible becomes significant. What was once a background effect becomes central. And eventually, the very act of observing begins to reshape the region we are trying to understand. Imagine trying to measure the surface of a calm pond by gently touching it with your finger. If your touch is light, the surface barely moves, and you can feel its shape clearly. But if you press harder, the water begins to ripple, distorting the surface beneath your hand. Press harder still, and the disturbance grows so large that the original surface becomes impossible to discern. You are no longer measuring the pond as it was. You are measuring the disturbance you created. This is the direction we are heading as energy increases. The act of observation, once gentle, becomes invasive. The region we are probing begins to change in response to our presence. And unlike the pond, where the disturbance eventually settles, here the effects can become permanent, reshaping the very structure of space itself. There is a quiet threshold hidden in this process, a point where the curvature of space becomes so strong that it no longer simply distorts paths, but traps them. Light, which normally travels freely, begins to bend inward. Paths curve back on themselves, and beyond a certain point, nothing can escape the region we have created. Not even the very signals we rely on to observe. This is no longer just distortion. It is confinement. The information we seek becomes sealed away, hidden behind a boundary that cannot be crossed from the outside. And the strange part is that this boundary is not imposed from elsewhere. It is created by the very energy we use to look deeper. The more we concentrate, the more we risk building a barrier around the thing we are trying to observe. At this stage, the familiar rule begins to break down. Increasing energy no longer guarantees better resolution. Instead, it begins to produce the opposite effect. The more we try to see, the less we are able to retrieve. Information does not become clearer. It becomes inaccessible. This is a profound turning point in our understanding. For so long, knowledge has been associated with effort. The harder we look, the more we learn. But here, that relationship begins to reverse. Effort itself becomes an obstacle. The very tools we rely on begin to limit us, not because they are insufficient, but because they are too powerful. And somewhere within this transition lies the emergence of a new kind of boundary. Not a physical wall, not a barrier we can touch, but a limit defined by the interaction between energy and space. A limit where observation and obstruction become the same act. We are not there yet, but we are approaching it. Each step deeper brings us closer to a point where the universe no longer yields to our curiosity in the way it once did. Instead, it responds with something quieter, something more absolute. A boundary not of matter, but of possibility. And as we move forward, that boundary will begin to take shape, not as an abstract idea, but as a concrete feature of reality. A scale where the rules we have trusted begin to transform, and where the question is no longer how to see smaller, but whether seeing smaller is even possible at all. Now we begin to approach the quiet edge where everything changes. Up until this point, the journey inward has followed a pattern that feels almost comforting. Smaller scales reveal deeper structure. Higher energy sharpens our vision. Even when the process becomes more violent, more indirect, it still delivers answers. But here, something subtle begins to unravel. Not in a dramatic collapse, not in a sudden failure, but in a slow and inevitable shift in how reality responds. Because the boundary we are approaching is not just about particles or forces. It is about space itself. To understand what happens next, imagine focusing an enormous amount of energy into a region so small that it becomes almost point-like. This is not something we can do in practice, but it is something we can imagine, guided by the rules we already trust. As we concentrate more and more energy into that region, the curvature of space grows stronger. What was once a gentle bending becomes a deep distortion. Paths that once passed through begin to curve inward more sharply, drawn toward the center. And then, something extraordinary happens. There comes a moment when the curvature becomes so intense that even light, the fastest messenger in the universe, can no longer escape. Any signal sent outward is pulled back inward. Any attempt to observe from the outside fails. The region becomes hidden, sealed off from the rest of the universe by an invisible boundary. This boundary is known as an event horizon, and what lies inside it is what we call a black hole. But here is the unsettling realization. In this context, the black hole is not a distant cosmic object formed from collapsing stars. It is something we have created ourselves, simply by trying to look too closely. The energy we use to probe a tiny region has become so concentrated that it has collapsed that region into a gravitational trap. This is the moment when the rule finally breaks. Before, more energy meant better resolution. Now, more energy creates a barrier. The very act of observation prevents observation. And beyond this point, there is no workaround. No clever technique, no alternative method, because the limitation is not in our tools. It is built into the structure of reality. What makes this even more profound is that this boundary is not arbitrary, can be estimated. There is a specific scale at which this transition occurs, where the energy required to probe a region becomes equal to the energy needed to turn that region into a black hole. And that scale is precisely what we call the Planck length. It is not just a small number. It is the point where two great pillars of physics meet and clash. On one side, quantum mechanics, urging us to look closer, to refine, to localize. On the other, gravity, resisting that localization, bending space more and more as energy increases. The Planck length is where these two tendencies balance perfectly, where neither can be ignored, and where their interaction creates a fundamental limit. At this scale, the idea of distance itself begins to lose its meaning. Because what does it mean to measure a distance if any attempt to do so destroys the very region you are trying to measure? What does it mean to define a position if the act of defining it creates a horizon that hides it from view? The familiar concepts we rely on begin to dissolve, not because they are wrong, but because they are no longer applicable. This is where the journey inward stops being about smaller things and becomes about the nature of reality itself. It forces us to reconsider what it means to observe, to measure, to know. Because if there is a limit beyond which observation cannot pass, then there is a limit to knowledge not imposed by ignorance, but by the structure of the universe. And yet, this limit is not violent. It does not announce itself with destruction or chaos. It is quiet. It simply prevents further access, like a horizon in the distance that you can approach but never reach. It defines a boundary of possibility. There is something almost protective about it, as if the universe is saying, you may explore, you may question, you may descend into the deepest layers of existence, but only up to a point. Beyond that, the rules change, not to punish curiosity, but to preserve coherence, to ensure that space, time, and energy remain balanced, even under the most extreme conditions. And so we arrive at a paradox. The more we try to see, the less we can see. The more precisely we try to define reality, the more it slips beyond our grasp. And this is not the end of the story. It is the beginning of a deeper question. Because if the Planck length marks a limit, we must ask what kind of limit it is. Is it a true boundary, the final edge beyond which nothing exists? Or is it something else entirely, a doorway into a different kind of reality, one that our current understanding cannot yet describe? As we move into the next segment, we will begin to explore this question more carefully, not by pushing harder, but by thinking differently. Because when direct observation fails, understanding must take another path. And perhaps in that quieter approach, we may begin to glimpse what lies beyond the limit that cannot be crossed. And so, we arrive at a quiet realization that feels both inevitable and deeply unsettling. For generations, the story of science has been one of progress through magnification. Better tools, higher energy, deeper insight. Each breakthrough seemed to promise that reality had no final layer, only finer detail waiting patiently to be uncovered. But now, standing at the edge of this journey, that promise begins to soften, not because it was wrong, but because it was incomplete. Because the universe does not simply allow infinite resolution. Instead, it sets a condition. You may look closer, but only if the act of looking does not destroy what you seek. And at the Planck length, that condition can no longer be satisfied. What makes this boundary so unique is not just that it stops us, but how it stops us. It does not block us with a wall. It does not present a surface we can press against or attempt to break through. Instead, it changes the rules in such a subtle way that the very question we are asking begins to lose meaning. We ask, what lies at a smaller distance? But if distance itself cannot be defined below a certain scale, then the question dissolves. It is like asking what is north of the North Pole. The language still works, but the concept no longer applies. This is the quiet transformation that the Planck length introduces. It does not tell us that there is nothing beyond. It tells us that beyond may not be a meaningful direction. And this is where the story becomes more philosophical, though still grounded in physics. Because if space cannot be divided infinitely, if there is a smallest meaningful unit, then space itself may not be continuous. It may not be a smooth fabric stretching endlessly in all directions. Instead, it may have a kind of structure, a subtle grain, invisible at larger scales but fundamental at the smallest. But we must be careful here. This does not mean space is made of tiny solid blocks like bricks in a wall. The reality is far more delicate. If there is a smallest scale, it is not something we can isolate, hold, or observe directly. It is a limit that emerges from the interaction of the deepest laws of nature. A boundary defined not by substance, but by possibility. And yet, even as this boundary closes one path, it opens another. Because if we cannot explore deeper by increasing energy, then perhaps we must explore differently. Instead of trying to see smaller, we begin to ask what kind of theories can describe a world where space and time themselves behave differently. A world where geometry is no longer smooth, where the familiar rules of distance and duration begin to blur. This is where new ideas begin to emerge, not from experiment alone, but from thought, from careful reasoning about what must be true if our current understanding is incomplete. Some of these ideas suggest that space is not continuous, but composed of discrete units, like a network woven from tiny connections. Others propose that the fundamental ingredients of reality are not points at all, but extended objects, small loops or strings that cannot be compressed beyond a certain size. In both cases, the message is similar. The infinite sharpness we once imagined does not exist. Reality, at its deepest level, may resist precision in a very fundamental way. And this resistance is not a flaw. It may be the very reason the universe is stable. Because if there were no limit, if energy could be concentrated without consequence, then nothing would prevent the collapse of structure at every scale. Atoms could not hold together. Space itself could tear under infinite stress. The existence of a limit may be what allows everything else to exist at all. So instead of seeing the Planck length as a failure, we can begin to see it as a kind of balance point. A place where the competing tendencies of nature meet and stabilize. Quantum mechanics with its desire to localize and refine. Gravity with its tendency to spread and curve. Together, they define a boundary that neither can cross alone. And within that boundary, everything we know unfolds. Stars burn, galaxies form, atoms bond, life emerges, all within a universe that quietly enforces its own limits. There is something almost comforting in that idea, not restrictive but grounding, a reminder that reality is not infinitely fragile, but carefully structured, held together by principles that prevent it from collapsing into chaos. And yet, even with this understanding, the mystery does not fade. Because knowing that there is a limit is not the same as knowing what lies at that limit. We have described the boundary. We have understood why it appears. But we have not yet answered the deeper question. What is the true nature of reality at that scale? Is the Planck length the final layer, the smallest meaningful unit of existence? Or is it simply the point where our current language breaks down, hiding a deeper structure that we have yet to uncover? As we move into the next part, we will begin to explore these possibilities, not by pushing harder against the boundary, but by stepping back and asking what kind of universe would naturally give rise to such a limit. Because sometimes, when a door cannot be opened, it is not meant to be forced. It is meant to be understood. And perhaps in that understanding, we will find that the Planck length is not the end of the journey, but the beginning of a completely different one. If you're still listening, gently let me know by commenting 1 below. There is a quiet shift that happens when a question changes its nature. At first, we were asking how small we could see. It felt like a technical challenge, something that better tools and higher energy might eventually solve. But now, standing at the edge of the Planck length, the question becomes something else entirely. It is no longer about improving resolution. It is about whether resolution itself still exists. Because what we discovered at the end of part 2 was not just a limit, but a reaction. The universe does not passively allow us to look deeper. It responds. And that response is gravity. For most of our everyday experience, gravity feels gentle, almost insignificant compared to other forces. It keeps us grounded, holds planets in orbit, shapes the motion of galaxies. But at small scales, we rarely think about it. Inside atoms, inside nuclei, gravity is so weak that it can be ignored. Other forces dominate completely. But this changes when energy becomes extreme, because gravity does not care whether its source is mass or energy. It responds to both. And as we concentrate more and more energy into smaller and smaller regions, gravity begins to grow quietly at first, then with increasing influence. It is like a presence that has always been there, unnoticed, slowly becoming impossible to ignore. At the scale of atoms, this effect is invisible. At the scale of nuclei, still negligible. Even in the most powerful particle accelerators we have built, gravity remains almost irrelevant. But as we imagine pushing beyond these limits, far beyond anything currently possible, we begin to enter a regime where gravity can no longer be dismissed. And when that happens, the rules begin to change. Instead of acting as a background force, gravity becomes a central player in the act of observation itself. The energy we use to probe a region begins to curve the space around it. Not metaphorically, but literally. The geometry of space starts to shift, responding to the concentration of energy like a fabric being pulled inward. This idea can feel abstract, but we can approach it gently. Imagine space not as an empty void, but as something with structure, something that can bend and stretch. When energy is present, this structure adjusts. Paths that would normally be straight begin to curve. Objects follow these curves naturally, not because they are being pulled in the usual sense, but because the space they move through has changed. Now imagine increasing the energy further. The curvature becomes stronger. The bending becomes more pronounced. And at some point, the distortion becomes so extreme that paths begin to close in on themselves. Light, which usually travels outward in straight lines, starts to curve back inward. Signals that would normally escape begin to return. The region becomes increasingly isolated, not by a barrier you can touch, but by the geometry of space itself. This is the beginning of what we described earlier as the black hole barrier. But here we are not talking about distant cosmic objects formed from collapsing stars. We are talking about something much more subtle, a limit that emerges naturally when energy is concentrated beyond a certain point. A limit that is not imposed from outside, but generated by the very act of observation. And this is where the story deepens. Because gravity is not acting against us in a hostile way. It is not preventing us from learning. It is simply enforcing consistency. It ensures that energy, space, and structure remain balanced, even under extreme conditions. But in doing so, it introduces a consequence we cannot avoid. The more precisely we try to define a region, the more energy we must use. The more energy we use, the more we curve space. And the more we curve space, the less accessible that region becomes. This creates a feedback loop, a quiet escalation where every attempt to gain precision leads to conditions that reduce it. And unlike earlier limits, which could be overcome with better tools, this one cannot. Because it is not about technology. It is about the fundamental relationship between energy and space. And so we begin to see the deeper pattern. Quantum mechanics encourages us to localize, to define, to sharpen. Gravity resists that localization, spreading and curving in response. At everyday scales, quantum effects dominate, and gravity is negligible. At cosmic scales, gravity dominates, and quantum effects fade into the background. But at the Planck length, these two influences become equal. And when they meet, neither wins. Instead, they create a boundary, a point where the very act of measurement becomes unstable, a place where the concepts of position and distance begin to lose clarity. And this is where the familiar world begins to dissolve, not into chaos, but into something we do not yet fully understand. Because if space itself is being reshaped by the energy we use to observe, then the idea of a fixed background, a stable stage on which physics unfolds, is no longer valid. The stage becomes part of the interaction. And when the stage itself is changing, the meaning of observation must change with it. This is the beginning of a new kind of thinking. One that does not treat space as passive but as dynamic. One that recognizes that at the deepest levels, we are not observing the universe from the outside. We are participating in it. And as we move further into this part, we will begin to explore what happens when this participation reaches its limit. When gravity no longer whispers, but defines the outcome entirely. Because beyond this point, the universe does not just respond, pushes back. As we move deeper into this strange territory, the idea of gravity as a distant, cosmic force begins to fade. It is no longer something that belongs only to stars or galaxies. Instead, it becomes something intimate, something that emerges even in the smallest regions when energy is pushed far enough. And what makes this so unsettling is how quietly it enters the picture. There is no clear boundary where gravity suddenly switches on. It grows gradually, almost invisibly, until it becomes the dominant influence. At first, the effects are subtle. A slight curvature, a faint bending of paths. But as energy continues to concentrate, the geometry of space becomes increasingly distorted. Distances begin to stretch in unexpected ways. What appears close from one perspective may be far from another. The idea of a fixed measurement begins to lose its certainty, replaced by something more fluid, more dependent on the conditions of the system. And then, at a certain threshold, the behavior changes completely. Instead of simply bending space, gravity begins to trap it. This is where the concept of an event horizon becomes more than just an abstract idea. It becomes a necessary consequence. When enough energy is confined within a sufficiently small region, the curvature of space becomes so extreme that all paths lead inward. Light, which normally escapes effortlessly, is forced to turn back. Information cannot leave. The region becomes isolated not by a wall, but by the structure of space itself. What is remarkable is that this threshold can be approached from two completely different directions. On one side, we have massive objects like collapsing stars, where gravity grows stronger as matter compresses. On the other, we have high-energy probing, where gravity emerges not from mass, but from the energy used to investigate smaller scales. Two very different processes, yet both lead to the same outcome, a boundary beyond which information cannot escape. This symmetry hints at something deeper. It suggests that black holes are not just rare cosmic accidents, but a fundamental feature of reality. They are what happens whenever energy, in any form, becomes too concentrated. Whether that energy comes from matter collapsing inward or from our attempts to probe deeper, the result is the same. A horizon forms, and beyond it, our ability to observe ends. And this leads to a powerful conclusion. There is a limit to how much information can be extracted from a region of space. Not because the information is not there, but because the process of extracting it changes the region itself. The more we try to access it, the more we risk sealing it away. It is a kind of self-protecting mechanism built into the fabric of the universe. But the story does not end with the formation of a horizon. Because once we accept that such boundaries can form at extremely small scales, we are forced to ask a deeper question. What happens to the information inside? In the classical picture, a black hole is simple. It is defined only by a few properties, like its mass and size. Everything else that falls inside seems to disappear from the outside world. But this creates a tension with quantum theory, which tells us that information cannot simply vanish. It must be preserved in some form. This tension becomes even more intriguing when we consider the microscopic horizons we are describing. If every attempt to probe beyond a certain scale creates a tiny black hole, then what happens to the information about the structure we were trying to observe? Is it lost? Is it encoded somehow on the boundary? Or is it transformed into something else entirely? These questions lead us into one of the deepest puzzles in modern physics. Because if information is preserved, then the horizon cannot be just a simple barrier. It must have structure. It must carry, in some way, the imprint of what lies within. And this idea begins to blur the line between inside and outside, between what is hidden and what is accessible. It suggests that the boundary itself may hold the key, that instead of thinking of space as something filled with information, we might need to think of information as something encoded on surfaces, on limits, on horizons. This is a radical shift, one that challenges our intuitive understanding of volume and depth. But it emerges naturally from the behavior we are beginning to see. And all of this traces back to a simple, almost innocent rule. To see smaller, use higher energy. A rule that guided us inward, step by step, until it transformed into something entirely different. A rule that now tells us that beyond a certain point, seeing more requires more than just energy. It requires a new way of thinking. Because the universe is not just a collection of objects waiting to be observed. It is a system that responds, adapts, and sometimes refuses. And as we continue, we will begin to explore what this refusal truly means. Not as an obstacle, but as a clue. A sign that the structure of reality is more subtle than we imagined. That the deepest layers may not be hidden behind distance, but behind the limits of how we define space itself. And perhaps, in understanding those limits, we will begin to see not just where observation ends, but where a different kind of understanding begins. There is a moment in every deep investigation when the problem quietly transforms. Not because we reach an answer, but because the question itself begins to resist being asked in the same way. Up to now, we have followed a clear path. We increased energy to see smaller structures. We discovered that energy bends space. We realized that beyond a certain point, this bending traps information, forming a horizon. But now, something even more subtle begins to emerge. A limit not just of observation, but of precision itself. Because what if the problem is not only that gravity hides what we are trying to see, but that reality itself refuses to be defined with perfect sharpness? This idea begins with a principle that has been quietly guiding physics all along. A principle so fundamental that it is not about technology, but about the nature of measurement itself. Whenever we try to determine exactly where something is, we disturb it. And the more precisely we try to fix its position, the more uncertain its motion becomes. This is not a flaw in our instruments. It is a built-in feature of the universe. At larger scales, this uncertainty is too small to notice. But as we move inward, towards smaller and smaller distances, it becomes impossible to ignore. The act of observation introduces a kind of softness, a blur that cannot be removed. Now, imagine combining this quantum uncertainty with the gravitational effects we have just explored. At first, the two seem unrelated. One describes limits on precision. The other describes how energy curves space. But as we approach the Planck scale, these two ideas begin to merge. And when they do, something remarkable happens. The uncertainty does not just remain constant. It grows. Let's move through this gently. To measure the position of something very precisely, we need to use a probe with a very small wavelength. That means higher energy. But as we increase the energy of our probe, we are also increasing its gravitational influence. And that gravitational influence begins to distort the region we are trying to measure. At low energies, this distortion is negligible, so increasing energy improves precision. But beyond a certain point, the distortion becomes significant. The more energy we add, the more space itself bends. And eventually, this bending introduces a new kind of uncertainty, one that comes not from quantum behavior, but from the geometry of space. So now, two sources of uncertainty are working together. Quantum uncertainty, which resists precise localization, and gravitational distortion, which disrupts the structure of space as we try to localize. At first, increasing energy reduces uncertainty, just as we expect. But then, something unexpected happens. There is a minimum point, a smallest possible uncertainty in position. Beyond that point, adding more energy makes things worse. The uncertainty begins to increase again. It is as if the universe allows us to sharpen our view only up to a certain limit. Beyond that, the act of sharpening causes the image to blur. This is one of the most delicate and profound ideas in modern physics. It suggests that there is a smallest meaningful distance, not just because of black hole formation, but because precision itself has a lower bound. And that bound aligns with the Planck length. This changes the story in an important way. Before, we thought of the Planck length as a barrier created by gravity, a point where observation collapses into a black hole. But now we see that even before reaching that extreme, something else is already happening. The universe is quietly preventing us from defining positions more precisely. Not through force, not through destruction, but through uncertainty. And this uncertainty is not random. It is structured. It arises from the interplay of the deepest principles we know. It is the result of trying to apply two powerful ideas at once, each valid on its own, but together creating a limit that neither could produce alone. This leads to a new perspective. The Planck length is not just a place where things break. It is a place where different aspects of reality balance each other. Quantum mechanics pushing toward precision, gravity pushing back against it, and in between, a minimum scale where both effects are equally important. At this scale, the very concept of a point becomes questionable. What does it mean to say something is located exactly here, if here cannot be defined with arbitrary precision? What does it mean to talk about distance, if the measurement of that distance introduces unavoidable distortions? The language we have relied on begins to stretch, and as it stretches, we begin to sense that something deeper lies beneath it. Perhaps space is not made of points at all. Perhaps the idea of infinitely small locations is simply an approximation, one that works well at larger scales, but fails when pushed too far. And if that is true, then the Planck length is not just a limit of measurement. It is a hint, a signal that the structure of reality may be fundamentally different from what we have imagined. As we continue, we will begin to explore what that structure might be, not by forcing sharper measurements, but by rethinking what space itself could be made of. Because when precision reaches its limit, understanding must take its place. There is something almost paradoxical about what we are beginning to see, because the deeper we go, the more the universe seems to guide us away from the idea of absolute precision, not by blocking us directly, but by reshaping the very meaning of what it means to measure anything at all. and this shift is so subtle that it can easily go unnoticed unless we slow down and follow it carefully, because what is happening here is not just a physical limitation, but a conceptual one, a quiet rewriting of the rules we have always assumed were fixed. Until now, we have treated space as something continuous, something that can always be divided further, like a line that can be split again and again without ever reaching a final piece. And this idea feels natural because it works perfectly at every scale we can directly experience, from the motion of objects to the structure of atoms. But as we approach the Planck length, this assumption begins to weaken, not suddenly, but gradually, as if the smoothness we rely on is only an approximation. Surface-level illusion that begins to dissolve when examined too closely. Because if there is a smallest meaningful distance, then the idea of dividing space endlessly no longer holds. And this does not mean that space suddenly becomes chunky in a simple mechanical way, like grains of sand, but rather that the concept of between starts to lose its meaning, as if there is a limit beyond which the distinction between one point and another cannot be made in any physically meaningful sense. And this is where our intuition begins to struggle, because we are so used to thinking of space as something infinitely divisible that the idea of a fundamental limit feels almost unnatural. But the universe has been hinting at this all along, not just through gravity, not just through uncertainty, but through the way information itself behaves, because as we learned earlier, when a region becomes too dense with energy, it forms a horizon, and that horizon seems to encode information not in its volume, but on its surface, and this suggests something deeply counterintuitive, that the amount of information a region can contain is not determined by how much space it has inside, but by the area that surrounds it. And if this is true, then space is not behaving like a simple container, but more like a system with built-in limits on how much can be stored within it. This idea, sometimes called the holographic principle, does not tell us exactly what space is, but it gives us a clue about what it is not, because if information scales with surface area rather than volume, then the intuitive picture of space as a vast empty interior filled with independent points begins to break down, and in its place we begin to see a more subtle structure, one where boundaries matter more than interiors, where limits define reality more than the regions they enclose. And when we connect this idea back to the Planck length, something remarkable emerges, because the Planck scale may not just be a limit of measurement, but a limit of information density, a smallest unit of meaningful distinction, beyond which no additional detail can be encoded, not because it is hidden, but because it does not exist in a form that can be separated from what surrounds it. And this shifts the question once again, away from what is smaller than this and toward how is information structured at this scale. This is where the picture becomes both clearer and more mysterious at the same time, because while we lose the ability to define precise positions, we gain a new way of thinking about reality, one that is less about points and distances, and more about relationships and connections, about how different parts of the universe relate to each other rather than where they are located in an absolute sense. And this relational view begins to feel more natural as we move deeper, because the old framework of fixed coordinates and continuous space no longer holds. And yet, even as this new perspective emerges, we are still left with a lingering tension, because we do not yet have a complete theory that fully describes this regime. We have pieces, hints, partial frameworks, each capturing part of the truth, but none providing a complete picture. And this is what makes the Planck length so fascinating, not just as a boundary, but as a meeting point of ideas, a place where multiple theories converge, each pointing toward a deeper structure that remains just out of reach. So instead of thinking of the Planck length as the end of the road, we can begin to see it as a kind of turning point, a place where the method of inquiry itself must change, where pushing harder in the same direction no longer works, and where understanding requires a shift in perspective, a willingness to let go of familiar assumptions and explore new ways of describing reality, even if they feel less intuitive at first. Because the universe is not simply hiding its deepest secrets, it is inviting us to rethink the way we ask questions, to move beyond the idea that everything can be understood by dividing it into smaller and smaller pieces, and to consider the possibility that at the deepest level, reality may not be built from parts in the way we expect, but from patterns, from interactions, from something that does not fit neatly into the language of size and distance. And as we move into the final segment of this part, we will begin to gather these ideas together, not to close the mystery, but to see it more clearly, to understand not just where the limits are, but what they might be telling us about the nature of the universe itself, because sometimes the most important discoveries are not about what lies beyond a boundary, but about why that boundary exists at all. As we gently reach the final stretch of this part, the picture that has been forming begins to settle into something both clearer and more mysterious, because what started as a simple question about how small we can see has slowly transformed into a much deeper realization about how reality itself is structured, and perhaps more importantly, about how our way of asking questions must evolve when we approach its limits, because the Planck length is not just telling us that we cannot go further. It is quietly teaching us that the idea of further may not apply in the way we once believed. If we trace the journey we have taken so far, a pattern becomes visible, one that feels almost like a conversation between two fundamental aspects of nature. On one side, quantum mechanics, always encouraging precision, always allowing us to refine, to localize, to zoom in with greater clarity. And on the other side, gravity, responding to that precision by bending space, by resisting confinement, by preventing energy from being compressed without consequence. And for a long time, these two influences seem to operate in separate domains, one governing the very small, the other shaping the very large. But as we approach the Planck scale, they begin to overlap, and in that overlap, something entirely new emerges. It is not a breakdown in the sense of chaos or disorder, but a kind of saturation, a point where adding more energy no longer produces more information, where increasing effort no longer yields deeper insight. And this is perhaps one of the most profound shifts in perspective, because it challenges a deeply rooted assumption that knowledge can always be expanded by pushing harder, by looking closer, by refining our tools. But here, that assumption reaches its limit, and beyond that limit, the relationship between effort and understanding changes. What we encounter instead is a balance, a delicate equilibrium where opposing tendencies cancel each other out, where the desire to define meets the resistance to being defined, and in that balance, a smallest meaningful scale appears, not as a physical object, not as a tiny building block we can isolate, but as a boundary in the space of possibilities, a point beyond which the concepts we rely on begin to dissolve. And this is why the Planck length feels so elusive, because it is not something we can point to directly. It is something that emerges from the interaction of deeper principles. And yet, even as this boundary limits what we can measure, it also reveals something unexpected, because it suggests that reality may not be infinitely detailed, that there is a finite amount of information that can be contained within any region. And this idea, subtle as it is, carries enormous implications, because it means that the universe is not an endless continuum of detail, but a system with structure, with limits, with an underlying organization that prevents it from becoming infinitely complex at arbitrarily small scales. This brings us back to a question that has been quietly present throughout our journey. Even if we have not fully addressed it until now, what is reality made of at its deepest level? If not infinitely divisible points, if not perfectly defined positions, then what remains when those concepts fade? And the answer, at least for now, is not a single theory, but a collection of ideas, each offering a different glimpse into what might lie beneath. Some suggesting that space is woven from discrete units, others proposing that the fundamental elements are not points but extended objects, and still others hinting that information itself may be the most basic ingredient, more fundamental than space or time. But regardless of which direction turns out to be correct, they all share a common theme, that the Planck length is not an accident, not a temporary limitation, but a reflection of something deeper, something that defines how reality organizes itself at the most fundamental level. And this realization changes how we think about the limits we have encountered, because instead of seeing them as obstacles, we can begin to see them as clues, as signposts pointing toward a new understanding that has yet to fully emerge. And perhaps this is the most important insight of all, that the universe is not simply hiding its deepest layers, but guiding us toward a different way of seeing, one that does not rely on infinite division, but on relationships, on patterns, on the interplay between energy, space, and information. Because when we reach the point where traditional questions no longer work, it is not the end of inquiry. It is the beginning of a new kind of inquiry, one that requires patience, imagination, and a willingness to let go of certainty. So as we prepare to move into the final part of this journey, we carry with us not just the idea of a limit, but a deeper sense of what that limit represents, not a wall that blocks us, but a threshold that transforms the way we understand reality. And beyond that threshold lies a question that is both simple and profound. If space cannot be divided endlessly, if distance itself has a smallest meaningful scale, then what is space actually made of? And is it possible that what we call space is not fundamental at all, but something that emerges from a deeper, more subtle layer of existence? We will explore that question next, slowly and carefully, not by forcing answers, but by allowing the ideas to unfold in a way that feels natural, because at this depth, understanding does not come from pushing harder, but from listening more closely to what the universe has been quietly telling us all along. If you're still here, gently let me know by commenting 2 below. There is a quiet shift that happens when we stop trying to force our way forward and instead begin to ask a different kind of question. Because once we accept that the Planck length cannot be crossed in the usual sense, we are left not with silence, but with possibility, a new direction of thought that does not rely on seeing smaller, but on understanding differently. And it is here, in this change of perspective, that some of the most intriguing ideas in modern physics begin to take shape. Because if space cannot be divided endlessly, if there is a smallest meaningful scale, then perhaps the very foundation of reality is not built from points at all. And this is where one of the boldest ideas emerges, the idea that the fundamental ingredients of the universe are not zero-dimensional dots, but tiny extended objects so small that they exist right at the edge of the Planck scale, and yet large enough, in a conceptual sense, to avoid the infinities that arise when everything is compressed into a single point. These objects are often imagined as extremely small loops or filaments, vibrating in different ways, and what makes this idea so powerful is not just its novelty, but what it resolves, because when particles are treated as points, interactions at extremely high energies become mathematically unstable, leading to infinite values that cannot be physically interpreted. But when those same particles are replaced with tiny extended structures, those infinities soften, the energy spreads out along the length of the object, and the equations become well-behaved once again. And this leads to a remarkable insight that perhaps the reason we cannot see beyond the Planck length is not because reality ends there, but because the idea of a point ceases to be meaningful, because there are no true points to observe, only tiny extended patterns whose behavior changes as we try to probe them more deeply. And this aligns beautifully with everything we have discovered so far, because instead of allowing infinite sharpness, the universe replaces it with a kind of built-in softness, a natural limit that prevents energy from collapsing into a single location. As we imagine probing such an object, something unexpected happens. Instead of revealing a smaller internal structure, the object begins to respond by changing its state, by vibrating more intensely, by expressing new patterns rather than new subdivisions. And this is a subtle but profound shift, because it means that increasing energy no longer leads to smaller distances, but to richer behavior, more complex modes of vibration, more possibilities within the same fundamental scale. It is almost as if the universe is redirecting our curiosity away from size and toward structure, away from where something is and toward how it behaves. And in this sense, the Planck length becomes not a barrier, but a transition point, a place where the nature of inquiry itself changes direction, where depth is no longer measured in distance but in complexity. And this idea carries a kind of quiet elegance, because it explains why the infinities disappear, why gravity emerges naturally, and why the Planck scale appears as a limit, all within a single framework, not by imposing boundaries from the outside, but by redefining what the fundamental elements of reality actually are. And in doing so, it offers a glimpse of a universe that is not built from static pieces, but from dynamic, vibrating patterns that give rise to everything we observe. But even as this picture begins to form, we must remain gentle with it, because it is not yet confirmed. It is not something we can test directly with current technology. And so it remains a possibility, a beautifully consistent idea that fits many of the clues we have gathered, but still awaits deeper evidence. And this is part of what makes this journey so fascinating, because at this scale, theory begins to lead, guided by logic, by consistency, by the desire to unify what we already know into a coherent whole. And yet, this is only one path, one way of interpreting the limit we have encountered, because there is another idea equally profound that approaches the same question from a completely different direction, not by extending particles into strings, but by questioning the nature of space itself, by asking whether space might be composed of discrete units, not continuous at all but built from tiny, indivisible pieces that connect together in a vast network. So as we continue, we will explore that possibility as well, not to choose between them, but to understand how each attempts to answer the same question: what lies at the foundation of reality when distance itself loses meaning? And how can we describe a universe that no longer behaves like a smooth, continuous stage, but something far more subtle, far more intricate, and perhaps far more beautiful than we ever imagined? As we continue this quiet exploration, the idea that reality might be built from tiny vibrating structures begins to settle into the background, not as a final answer, but as one possible path. And now we turn gently toward a different vision, one that does not begin with particles at all, but with space itself, because if the Planck length marks a limit to how finely space can be divided, then perhaps space is not continuous, not infinitely smooth, but composed of something more fundamental, something discrete, something that exists in small, indivisible units that together create the illusion of continuity. At first, this idea can feel unfamiliar because everything in our daily experience suggests that space flows smoothly, that you can move from one point to another without ever encountering a smallest step. But this intuition is built on scales far removed from the Planck domain, and just as matter once appeared continuous before we discovered atoms, space itself may only appear smooth because we are observing it from too far away, unable to see the underlying structure that gives rise to that smoothness. In this alternative picture, space is not a passive stage where events unfold, but an active structure, something that has its own smallest building blocks, not like bricks in a wall, but more like nodes in a network, connected by relationships that define how regions of space relate to each other. And instead of thinking of space as something that exists independently, we begin to think of it as something that emerges from these connections, from the way these fundamental units interact and organize themselves. Imagine for a moment that space is like a vast web, where each point is connected to others through invisible threads, and each connection carries information about distance, geometry, and relation, and at large scales, this web appears smooth, continuous, almost effortless in its structure. But as you zoom in closer and closer, the individual strands begin to reveal themselves, the connections become discrete, and the illusion of continuity fades into a more granular reality, one that is still coherent, still structured, but no longer infinitely divisible. What makes this idea so powerful is that it does not just explain the Planck length as a limit, it explains it as a natural consequence, because if space is built from discrete units, then there is a smallest possible area, a smallest possible volume, a smallest meaningful distance, not because we cannot measure smaller, but because smaller does not exist in the same way. And this aligns beautifully with the idea that at the Planck scale, distance loses its meaning not as a failure but as a reflection of how space is actually constructed. And just as with the previous idea of extended objects, this framework also avoids the infinities that arise when we treat everything as continuous, because if space itself has a smallest unit, then it cannot be compressed indefinitely, it cannot collapse into a singular point of infinite density, and this has profound implications for some of the deepest problems in physics, including what happens at the center of black holes or at the very beginning of the universe, because in this picture, those singularities may not exist at all, replaced instead by regions where space reaches its smallest possible configuration and then transitions into something else. There is something deeply calming about this idea, because it replaces the notion of infinite collapse with one of stability, of balance, of a universe that has built-in safeguards against its own extremes, and this echoes what we have been seeing all along, that the Planck length is not just a barrier, but a point of equilibrium, where different aspects of reality come together and prevent further breakdown. But even here, we must remain careful, because while this picture is elegant, it is still a theory, a way of describing what might be true rather than what has been definitively proven. And like the idea of vibrating structures, it offers consistency. It aligns with many of the clues we have gathered, but it remains part of an ongoing search, a collective effort to understand what lies beneath the surface of everything we observe. And yet, what is most fascinating is that despite their differences, these two approaches, one based on extended vibrating objects, the other on discrete units of space, both lead us to a similar conclusion, that the Planck length is not arbitrary, not accidental, but deeply woven into the structure of reality. A scale where our familiar concepts give way to something new, something that does not fit neatly into the categories of continuous or discrete, but perhaps exists in a space between those ideas. And this convergence is not something to overlook, because when different paths lead to similar insights, it often means we are circling around a deeper truth, one that has not yet fully revealed itself, but is beginning to take shape through the patterns we are uncovering. And in this case, that truth seems to be pointing toward a universe where space, time, and information are not separate ingredients, but aspects of a single underlying structure, something more fundamental than any one concept alone. So as we move forward, we carry with us not just one idea, but a collection of perspectives, each offering a different way of seeing the same mystery. And together, they begin to form a more complete picture, one that suggests that the Planck length is not the end of understanding, but the threshold where understanding must evolve, where the language of physics must expand to describe a reality that no longer behaves in familiar ways. And in the next segment, we will begin to explore one of the most intriguing consequences of this shift, the idea that information itself may be the true foundation of the universe, and that what we perceive as space and time may emerge from something even deeper, something that does not exist in any location, but gives rise to all locations, quietly, consistently, and beyond the limits we once thought were final. As we move even deeper into this final stretch of understanding, something quietly remarkable begins to emerge, not as a sudden discovery, but as a gentle shift in perspective, because up to this point, we have been thinking of space as the foundation of everything, the stage on which reality unfolds, the container that holds matter, energy, and time. But what if this intuition is reversed? What if space is not the foundation at all, but something that emerges from a deeper layer, something built not from distance, but from information itself? This idea may feel abstract at first, but it arises naturally from everything we have already explored, especially from the strange behavior of horizons, because when we considered what happens at extreme energy densities, we found that information does not behave the way we expect. It does not fill a volume in the usual sense, but instead seems to be encoded on surfaces, on boundaries, and this suggests that the true description of reality may not be about what is inside a region, but about how information is organized at its edges. Imagine, for a moment, that the universe is not a vast empty space filled with objects, but a network of information, where every physical property, every position, every interaction is the result of underlying relationships. And in this picture, space itself becomes something that emerges from those relationships, not something that exists independently, but something that arises from the way information is connected, structured, and shared across the system. This changes everything in a very quiet way, because it means that distance is not a fundamental quantity, but a derived one, something that comes from how strongly different parts of the system are related. And in this sense, 2 points that are close are simply more strongly connected, while points that are far apart are less connected. And this idea transforms space from a static backdrop into a dynamic network of relationships, constantly evolving, constantly shaped by the flow of information. And when we bring this idea back to the Planck length, it begins to make even more sense, because if space is emergent, then there must be a limit to how finely these relationships can be defined, a smallest unit of distinction, beyond which the concept of separation no longer applies, and that limit naturally aligns with the Planck scale, not as a physical boundary, but as a limit of meaningful differentiation, a point where the network cannot be refined any further without losing coherence. In this view, the Planck length is not a wall in space, but a resolution limit of reality itself, similar to how a digital image has a smallest pixel size, not because the image ends there, but because that is the scale at which the information is defined, and trying to zoom in further does not reveal new detail, it only reveals the structure of the pixels themselves. And perhaps in a similar way, when we try to probe beyond the Planck scale, we are not uncovering new layers of space, but encountering the underlying structure from which space emerges. This perspective also helps resolve some of the deepest puzzles we have encountered, because if information is fundamental, then the behavior of black holes becomes less mysterious. The idea that information is preserved on horizons begins to feel natural, and the tension between quantum mechanics and gravity starts to soften, not because one replaces the other, but because both are seen as different aspects of a deeper informational framework. There is something profoundly elegant in this idea, because it unifies many of the clues we have gathered: the limits of measurement, the emergence of horizons, the quantization of space, the behavior of energy at extreme scales, all pointing toward a universe where the deepest layer is not made of things, but of relationships, not of objects, but of patterns, not of positions, but of connections. And yet, even here we must remain grounded, because this is still a developing area of thought, a direction that many physicists are exploring, but not one that has been fully confirmed, and so we hold it gently as a possibility, as a way of seeing that fits the clues we have, while remaining open to whatever future discoveries may reveal. But even without final answers, this shift in perspective offers something valuable, because it allows us to reinterpret the Planck length not as a frustrating limit, but as a meaningful feature, a sign that reality is structured in a way that prevents infinite detail, that organizes itself around finite information, and that invites us to think not in terms of smaller and smaller pieces, but in terms of deeper and deeper relationships. And perhaps this is the quiet message that has been unfolding throughout this entire journey, that the universe is not something we can fully understand by breaking it apart indefinitely, but something we must learn to understand as a whole, as an interconnected system where limits are not obstacles, but guides, pointing us toward a more complete picture of what existence truly is. As we move into the final segments, we will begin to gather these ideas into a calm reflection, not to resolve every mystery, but to appreciate the shape of the questions themselves, because sometimes the most profound understanding comes not from finding a final answer, but from seeing clearly the boundaries within which all answers must exist. As everything begins to come together, there is a quiet sense that the journey has not been about reaching a final answer, but about gradually reshaping the way we understand the question itself, because what started as an attempt to look deeper into space has slowly revealed something far more subtle, that space may not be the deepest layer at all, and that the limits we encounter are not failures, but reflections of a deeper structure that holds everything in balance. If we pause for a moment and look back, we can see how each step has led us here, how the simple idea that higher energy reveals smaller detail guided us inward, how that rule began to bend under the influence of gravity, how uncertainty emerged not as a flaw but as a fundamental feature, and how all of these threads converged at the Planck length, not as a stopping point, but as a place where multiple aspects of reality meet and redefine what is possible. And now, standing at this threshold, the question is no longer how to go further, but how to understand what we have already reached. Because the Planck scale is not empty, it is not a void beyond knowledge. It is a region where our familiar concepts dissolve and must be replaced with something more refined. Something that can describe a reality where space, time, and information are no longer separate ideas, but deeply intertwined aspects of a single underlying structure. There is something almost poetic in this transition, not in the emotional sense, but in the way it reveals a hidden symmetry, because the same principles that limit our ability to observe also ensure the stability of the universe. The same constraints that prevent infinite precision also prevent infinite collapse. And this suggests that the limits we encounter are not arbitrary, but necessary, part of a deeper balance that allows complexity to exist without unraveling. In this light, the Planck length becomes something more than just a number. It becomes a kind of anchor, a scale that defines the smallest meaningful structure in the universe, not because nothing exists beyond it, but because beyond it, the very framework we use to describe existence must change. And this idea invites us to think of reality not as something that extends infinitely in all directions, but as something that is carefully structured, with built-in limits that preserve coherence at every level. And perhaps this is why every path we have explored, whether through extended structures, discrete geometry, or informational frameworks, leads to the same conclusion, that the universe resists infinite division, that it replaces sharpness with structure, that it trades absolute precision for stability, and in doing so, it creates a world that is not only understandable, but capable of supporting everything we observe, from the smallest particles to the largest cosmic structures. But even as this understanding begins to settle, there is still a quiet mystery that remains, because knowing that there is a limit does not fully explain why that limit exists in exactly the way it does, why the Planck length has the value it has, why the balance between quantum mechanics and gravity takes this particular form. And these questions remind us that while we have come far, there is still more to uncover, not by forcing our way deeper, but by refining our understanding of the principles we already see. And this is where the journey becomes more reflective, less about discovery in the traditional sense, and more about integration, about seeing how the pieces fit together, how the limits, the uncertainties, the structures all combine into a coherent picture of reality. One that is not infinite in its detail, but rich in its relationships, not boundless in its divisibility, but complete in its organization. So instead of imagining the Planck length as a final wall, we can begin to see it as a kind of horizon, not one that blocks our view, but one that defines the edge of a certain way of seeing, beyond which a different perspective is required. And this shift in perspective may be the most important step of all, because it allows us to move beyond the idea that understanding comes only from breaking things into smaller pieces, and toward the realization that sometimes understanding comes from seeing how those pieces are connected. And as we approach the final segment, we will let this perspective settle into something calmer, something more reflective, not as a conclusion, but as a quiet appreciation of what the journey has revealed. Because in the end, the Planck length does not close the story of the universe. It deepens it, inviting us to explore not just what reality is made of, but how it holds together in a way that allows us to ask these questions at all. And now, as everything gently settles, we arrive not at an ending, but at a quiet horizon of understanding, where the urgency to push further begins to fade and is replaced by something softer, something more reflective, because what we have uncovered is not a final layer of reality, but a boundary that reshapes how reality can be known, and in that realization, there is a kind of stillness, as if the universe itself is inviting us not to force our way beyond, but to pause and simply observe what is already here, because the Planck length, for all its mystery, is not loud. It does not announce itself with explosions or dramatic transitions. It exists quietly beneath everything, defining the smallest meaningful scale without ever needing to be seen directly. And perhaps that is what makes it so profound, that something so small, so far beyond direct experience, can influence the structure of everything we know, from the behavior of particles to the evolution of the cosmos itself. And if we allow ourselves to sit with that idea for a moment, it begins to feel less like a limitation and more like a kind of balance, a gentle boundary that keeps the universe from collapsing into infinite complexity or dissolving into complete uncertainty, a point where opposing forces meet and hold each other in place, creating a stable foundation upon which everything else can emerge. Because without such a limit, without a smallest meaningful scale, there would be no anchor for reality, no way to prevent energy from concentrating without bound, no way to ensure that structures remain coherent across time. And so what first appears as a restriction reveals itself as a condition for existence itself, a quiet rule that allows the universe to be both rich and stable at the same time. And yet, even with this understanding, the mystery does not disappear, it simply changes shape, because the question is no longer what lies beyond the Planck length, but what kind of reality gives rise to such a limit in the first place, what deeper principles, what underlying structure, could naturally produce a universe where space, time, and information all converge at a single scale, and then gently refuse to go further. Perhaps the answer lies not in smaller distances, but in deeper relationships, in the way different parts of the universe connect and interact, in patterns that do not depend on size at all. And if that is true, then the Planck length is not the end of the journey, but the place where the journey changes direction, where we stop looking inward through smaller and smaller scales, and begin looking outward through broader and more integrated ideas. There is something quietly comforting in that shift, because it reminds us that understanding does not always come from going further. Sometimes it comes from seeing more clearly what is already within reach, from recognizing the patterns that have been there all along, waiting not to be discovered through force, but to be understood through attention. And so, as this journey comes to rest, we are left not with a final answer, but with a deeper sense of connection to the structure of reality itself, a sense that the universe is not endlessly divisible, but thoughtfully composed, not infinitely detailed, but carefully balanced, and that within this balance lies the reason we are able to ask these questions at all. If you imagine the universe now, not as an infinite void, but as something gently structured, with limits that protect its coherence, with relationships that define its form, with a smallest scale that anchors its existence, then the Planck length begins to feel less like a boundary and more like a foundation, a quiet note at the base of everything, too subtle to hear directly, but essential to the harmony of the whole. And as your thoughts begin to slow, and the questions soften into something calmer, you may notice that the need to reach beyond that boundary begins to fade, replaced by an appreciation for the depth that already exists within it. Because sometimes, the most profound understanding is not about what lies further, but about what lies quietly beneath everything we already see. So let the idea rest there, gently, without needing to resolve it completely, without needing to push it further, just allowing it to exist as part of the larger picture. A reminder that even at the smallest scales, the universe holds its structure with quiet precision, inviting us not to conquer it, but to understand it slowly, patiently, and with a sense of calm curiosity. And if you're still here, still listening as the thoughts begin to drift, let me know softly by commenting 3 below, and wherever you are in this moment, whether near or far, may the quiet structure of the universe bring you a sense of stillness as you rest.